Thank you very much. It's a great honor given to me to invite me to this meeting here. And my task here is to say something about the history. History, I am going to explain mostly just one technique, little less known. It is the modulated gradient spin echo. In fact, just to say the history, I started with NMR many years ago. In 1963, I finished my diploma work with APR. Then I moved to ferroelectrics, doing NMR of that one. And in 73, I went to postdoc in United States. And after postdoc at United States, actually, this history of this method started. So let's go. So everything is happening in Ljubljana. It is area view to my city. I was working mostly at the University of Ljubljana and Jožef Stefan Institute. And what is the modulated gradient spin echo? This is technique which makes possible to measure velocity autocorrelation function. This quantity is the key quantity for molecular dynamics in the system. And NMR and modulated gradient is one of the rare techniques which makes possible to measure this quantity directly. Another technique is neutron scattering, inelastic neutron scattering. But these techniques cover mostly the range above the gigahertz, very short times, and actually the frequency range above the gigahertz. But these techniques I'm going to explain is modulated, can cover the range, low frequency range. So far we reach 10, 20 kilohertz. I believe it can go further on, and I can show you quite interesting results. So first, actually, modulated gradient techniques work so that you modulate the phase of the spin such a way, moving up and down very quickly. And it provides a kind of stroboscopic view to the molecular motion in such a way. So the history is such that in 1975, then I went to postdoc in United States. I explain later. This formula appears. Where attenuation of spin echo is related to the spectrum of the velocity autocorrelation function. Later, actually, it was just idea. It was a story developed, but almost 20 years later, actually, first experiment confirms this idea that really we can explain that attenuation is related to, in such a way, to the spectrum of the velocity correlation function. And nowadays, this method is still developing. Now we are able to go out. Before we've been able only to measure to the about 1 kilohertz, this spectrum of the velocity correlation spectrum. Now we can go to 10, 20, and even higher. But let me say why this is important. What is the velocity autocorrelation? What kind of information can provide? Let's look to this picture. I borrowed this picture from a presentation given by these people here in Leipzig meeting about the NMR. You have the same picture, diffusion weighted NMR, you can see here, diffusion weighted NMR, interpreted in different way. This one is using apparent diffusion. Kurtosis means deviation from this linear dependence. You can explain this by this technique, say anomalous diffusion. You can also use the propagator, as Jörg just explained it, what it is. But what kind of information about the motion we can get from this data? Here we have the picture of this alpha. You can see here, and what is this here is another picture. Here you can picture of apparent diffusion and deviation from the apparent. And what kind of information of the motion we can get from these pictures. Let's go to definition. It is Einstein's definition of the diffusion. Diffusion, the coefficient is time derivative of the mean square displacement in the infinite time. And of course, we can also relate this mean square displacement to also to the velocity of correlation. This is just normal. You know, when you have displacement, you can also displacement calculate the velocity. And here is the relation between the mean square displacement correlation function. But we never measure everything in infinite time. According to the Einstein definition, we should go to infinite time with these gradient pulses to get proper information about the diffusion coefficient. Of course, when processes are very fast, even this few milliseconds is enough for infinite. But generally, especially in restricted diffusion, we are not measuring the real diffusion coefficient, but something else. And finite time of measurements means we got apparent diffusion coefficient. But these two equations actually can give another definition. You just simply put it here. You get that diffusion constant is just integral of the velocity to correlation function from 0 to infinity. It's Green-Kuber relation. And velocity correlation function is this function that we can get simply from the second derivative of mean square displacement in time. But what is the velocity correlation function? Actually, this looks time dependence of the velocity correlation function in time. In liquids, you have very strong interaction between more molecules. So molecules forget very quickly what happens in the previous moment. It happens that molecules remember this collision between other molecules in a time of nanoseconds. So it's something which cannot be measured by NMR because we are measuring in the range of milliseconds, something like that. And for that reason, for point of view NMR, this function here is just a kind of delta function. But let's go to restricted diffusion. We have taken just make a box, close in the box these molecules here, and now this form of diffusion is changed. There appears a long tail. First part gives you something about interaction between molecules, but the second part gives you how long molecule remember collision with the walls. So it lost quite a long now, and it might be measured by NMR. But so this velocity correlation includes information about the underlying interaction between molecules in different ways, between molecules or between molecules and the walls. And looks to the spectrum. Spectrum of liquids, for example, it is very fast decay. It is in this range completely flat, and this range, which is in gigahertz region, it can be measured. By NMR, we can measure only this part. Somewhere about kilohertz, 10 kilohertz, something like the shortest, and just Fourier transformation of this function gives you the spectrum, of course. And general definition of diffusion constant is just zero, where the spectrum at the zero frequency, as you can see here. What about the restricted diffusion? These long tails bring you that that in this region of the frequency spectrum is going down, and it is just in the range of NMR. Of course, we are working in range of NMR, even using pulse sequences or for the pulse gradient spin echo or something else. We are always in this regime, and we always get something from about this. So that is something. No, and this is just an explanation of what is the velocity autocorrelation function at spectrum. And I was on postdoc in United States in Seattle, and I got a task. It is they gave me just equipment. It is old-fashioned continuous wave NMR. I don't know how if you understand what it is. Continuous wave work completely differently. And I got a task: try to find a way to measure diffusion by this equipment. So far, that time nobody knows, and this method works such a way that you have the resonance coil in the constant frequency, and you move actually the magnetic field through the resonance line. resonance line here, and then appears the signal, and you can get here the signal, and it was very easy also not to measure at that time just the protons or a hydrogen. We can measure by this natrium, silicium, and so on. And thus given to me, find a way to measure cell diffusion of ions in beta alumina solid electrolytes. Find a way. I didn't know what to do. I simply say, okay, let's try to replace this modulation. You have seen additionally to this field, which was changing, you apply some modulation of magnetic field. The reason was quite simple. Instead to get DC signal when you cross the resonance line, you get the signal which is also modulated. It's much easier to detect. Detect it in some higher frequency and you decrease the signal to noise ratio that way. And I said, let's try to replace this modulation by the magnetic field by the gradient field. So instead, this green line means now we have inhomogeneous magnetic field. And that time I studied it, we studied together. I was working with John Bjorkstam in HEV. And that time I tried first to solve Bloch-Tauler equation or something like that. But it didn't work. But later when I came home, I went a little more precisely through this theory, solving the quantum mechanically, density metric, and so on, and appears this formula from here. It has me very much this paper of Rigo Kugo about the cumulant expansion, how to actually average the phase modulation of the spin phase. It was published in '81, this idea, and of course what it means. It means that instead to describe attenuation with some apparent diffusion, actually exact calculation should be something like that. It's like that, and here it is spectrum of the spectrum is here, and this part here, Q, is how you modulate your spin phase. You can modulate spin phase in two ways. Changing the gradient, applying, for example, oscillating gradient, or maybe applying the RF sequence. RF sequence, and all together should produce this spectrum here in such a way that you extract the value of the spectrum of velocity correlation from here. No, it was such idea, it was a paper. Later I was involved in some other project doing ultrasonics and Earth magnetic field NMR and so on, and it came. No, I had to mention that only paper I found for NMR that somebody used relation between velocity correlation function and spin echo was the Gen in a paper, but it was not, this formula was not derived. But in year 1991, I was surprised that this idea and the derivation as well as formula appeared in the book of Paul Callahan. And I met soon after that in '91 in some meeting in Slovenia, and Paul Callahan offered me, come to my lab and we are going to check if your method works. I tried to do this even before in my group because we had also the group doing the diffusion, but I was not interested to check this idea. But Callahan offered me this, and he invited me and spent my sabbatical in his lab, 94, 95, that time. And we quickly find the techniques by my method which can provide spectrum of the velocity correlation function. It is just CPMG sequence and the train of pulses here applied in the between. I'm not going to show it a little later what such kind of sequence what can produce, how we can do this. And we test this technique simply just with the flow through the sand, you know. In the sand, it was ion exchange resin. Actually, the flow, it was not, we didn't measure the flow, the velocity of flow, but mostly the turbulent motion, how the fluid is moving around the beds. And this was a spectra. Slow motion, slow flow gives us something like that, fast, something like that. And it was first test. Sarah Cott, she's also here, has done. It was just one experiment I have done with Paul Callahan, but Sarah has done a lot in this direction and quite interesting result about that. And from our measurements at that time also came out not just flow, but it was simply just spectrum of the velocity correlation function on the porous media. Porous media, we use here quite big bits, 15 microns, and we get some drops here. I have shown before it that it should happen at the low frequency regime. It was mostly, this is written in this review paper, the much more precise measurements of this using this sequence has been done by the group of Lund, University of Lund. It is a paper of Daniel Topgaard, he's here, Ole Soderman is also here. They try to apply these techniques to measure restricted diffusion in the emulsion droplets. And it is just free water, they get something like that. And he says, this is a fresh emulsion where droplets are pretty small, about micron, and then after a certain time these droplets join and it's get bigger, and they get something. It is expected with such a restricted diffusion. Only problem was with the frequency range. Frequency range was limited using such a sequence to below 1 kilohertz. Why? Induction of the gradient coil, of course. We cannot switch gradient coils faster than that. Now, another guy who tried to use the same idea, the same formula, was Edward Parsons from the John Gore lab. He actually made a lot of measurements. Instead of using CPN sequence and gradient pulses, he applied the oscillating gradient. Oscillating, they also call this, we call this modulated gradient method. It is actually named, given by Paul Callahan. I have respect to him, I want to keep it this name. But this is oscillating. But there appears the same problem. They measure this in different size of the bits, from 100 micron down, and this one, the last one, is 1 micron. But you can see, if you're approaching very short 1 micron, you have a lot of noise. You have a lot of noise at a high frequency, about 500 hertz, and also signal is not very strong. So main problem is high frequency limit, limited by the gradient coil induction. If you look to this review paper I already mentioned before, we published with Paul Callahan, actually this is method which we first experiment, where we also propose techniques where you are not switching the gradient. Gradient is constant. But by the time we've been afraid what happens when you apply simultaneously the gradient, constant gradient, and the RF pulses. We expect that there should some resonance artifacts can appear. Later, especially actual work of my colleague Samo, who is also here. He has done a PhD degree on this problem. We try to apply this sequence first to measure velocity correlation function of fluidized granular system. He has done a lot of simulations and so on. It appears for this simulation there is no any problems applying such a gradient and simultaneously the RF pulses. So, but if you want to be sure what it happens, we have to make the precise calculation, not just simulation. So I'm just going to I just want briefly to explain how it can be calculated. Actually, using normally spins are quantum particles, you have to deal with Hamiltonian, and here is main field, inhomogeneous magnetic field, area field, and the rest. You can include here also interaction with chemical shift, quadrupole interaction, and so on, and you can deal. But here we are assuming that gradient is strong, so strong that this term here prevails. And just calculation, transformation of the system into rotating frame and in the toggling frame, because the spins are all the time moving due to the p pulses all around. It's end up that our effective Hamiltonian, it is consists only of two parts. One part actually is some cosinus. Here you have BT mean how its effect, because RF pulses all the time change the phase for pi if you're applying. And of course, if you change this for the pi, it means the cosinus is moving from 1 to -1, from 1 to -1, but it's going, because pulses are not infinitely short, it has finite width. It means that at the reason appears something which produce so-called resonance offset effect. It can actually produce some artifacts in your picture, but we have made calculation with this one, and we notice that there is some effect. We understand this effect and how to get rid of this effect for such kind of measurement. So this method can work in such a way. It means we get here the phase modulation, and my further explanation, I forget this one, and I assume that only exists this modulation, effective modulation of the gradient. It's going up and down in such a way. And if we want to measure the signal, actually this term gives you the phase. The phase of the signal, how it's changing. This formula is identical for imaging, for everything you do. But if you are just interested what happened to the peak of spin echoes, this peak, it means n tau, I mean it's just position of the peak here. So we can do the par-parts integration of that one. Par-part integration means that you replace here this part with time derivative, this is integral, and so we get here that this modulation here going, because it's integral, is going up and down, and it is actually the modulation which I show you at the very beginning. But what is important in this formula, and if you're looking just to the peak of spin echo, here appears velocity. So it means in the peak of the spin echo, velocity of particle is encoded. It is written there. You need just how to actually analyze and how to measure. You can show you how we can from here we can go to the spectrum velocity correlation function. Actually, we have many spins, so summation, and we have to also to make an average, time average, during the time of our measurements. To 1 echo second and so on, all this time is important. And in this paper and maybe other textbook about the stochastic processes, you can find that such an average you can expand in cumulants. In cumulants, it means first term it's a kind of Taylor expansion, but it's expansion in cumulants. First term is average velocity. Second term is correlation of velocity. And if you're satisfied with Gaussian phase approximation, it has been done, and some people say it's not enough that you expand just to two terms. Should be taken into account more terms, but as long displacement of particles is shorter than the phase grating created by the gradient, as long this approximation perfectly works. You have just two terms. One term is the phase, change of the phase of the signal, second term is the attenuation. And now we transform this correlation function, this in Fourier transform, in such a way that is now spectrum. I have to mention here that this velocity correlation is a tensor. Is a tensor in the system. That if you have anisotropic system, you should take into account this. And this is a part which comes from this function ft, and all together give us attenuation. So this is our formula. Now if we applied such kind of sequence, just going up and down here, spectrum is quite simple. Dominant is just it's a kind of delta function, which is dominant peak at very big at the resonance of modulation, how it's going up and down. So I have to mention this term is also important sometimes, especially if you're working, for example, with the pulse gradient spin echo. This term produces so-called diffusive diffraction. Diffusive diffraction, not through the propagator, it is normally, but actually this term, first one is responsible. But when you switch this dephasing so fast, this term is averaged out. So you can sure that if you now put this delta function in this equation, your echo is simply directly diffusion attenuation directly proportional to the diffusion spectrum at the modulation frequency, and this is actually shown how it works. When the change interval between pulses, this delta function here is moving across the line, and of course a different tau, different interval, it means different frequency, we can pick up the value of this one, of this diffusion spectrum. And this is the first measurements we had done on such system, water in silica powder. We notice really we get simply something like that, and we have a strong deviation. It means we didn't have the silica powder with the big distribution of the pore size. From here we can also get information of surface to volume ratio. I'm not going into details. And theory is very well known for this theory. How it looks, spectrum of velocity correlation function for restricted diffusion. It was shown already in the Tanner's paper at the very beginning. It was developed that time. So we have here, for example, you have summation from many k. But it is shown, for example, for the spherical geometry. You can see here that exact calculation is the blue line and approximation is not. Approximation is below, so in this region is not important. And you can see that this B key means is a parameter of the structure, and tau here is in fact characteristic time. Characteristic time is proportional to the time of light across the pore boundaries. For other geometry, for plumb parallel, for cylindrical, you can get a very similar formula, only this structure parameter is different. And we believe that such kind of formula you can apply quite generally, and maybe measurements give you actually the value of structure parameter, not simple calculation. And this is, for example, measurements at hydrogels. I shown just one example. We had done many measurements, and from using this formula, we calculate here what the size of the pore. Through this formula, what the tortuosity, what it means, what's the permeability of this sample. This is idea. So method works. But this method works with the constant gradient. But the constant gradient is also appear in the porous structure due to susceptibility difference. Bits and at the interfaces between the bits and the liquid appear some additional field. It is called internal. And here's an example. You have bits, and all around you have some additional field. This dark and bright region means difference in the field. And we have done experiment in such system. It was we used some. It was ceramic, prepared identical way, 5 pieces. In addition to that, we add paramagnetic impurities to be sure that not measuring just internal field due to susceptibility, but also field which is produced with the paramagnetic impurities. And so internal fields consist of two parts, stability and magnetic impurities, and measurements on the sample prepared in the identical way, and diffusion of water in this pore, in such a sample, a different concentration of the impurities. You get points. This is for lower, high, and so we have changing concentration paramagnetic impurities, and it can be very fitted. This is formula I have shown you before. And from here, we can get actually relaxation time, pore size. Pore size is actually here between 0.4 to 2 microns. And electron microscopy said that its pore size is between 2 and 3 micrometers. It means our measurements are much more perfect. The scientists found measuring independently susceptibility, and here is the ratio of susceptibility and the internal gradient we get from our measurements. It is almost flat, it's almost constant. It's a part. And we apply these techniques for the early hydratation process of cement paste. But we can see how the pore size is changing with time, how internal gradient is changing at his relaxation time. So it means this method makes possible also to measure with the use of internal fields. And this is an example how apply to these techniques for imaging. It is polenta. Polenta cooking up to 2 minutes. T2 weighted diffusion with, weighted with the PGS and with the actually these techniques. We use 100 and 1 kilohertz, something like that. There is some differences between these two pictures here, we can see them. And it can be because we get different kind of information, depend on which side of the spectrum, but here also be something else. Diffusion spectrum is a tensor, and this tensor depends on pore structure. If we use some tube, maybe capillary, for example, try to measure here, so that we're changing the direction of the constant magnetic field, rotating all around. What we get from such picture? We get actually the picture of the diffusion spectrum tensor here. And of course, this is a way how, for example, if we are working, for example, a constant frequency and measuring, we can see that this is a constant frequency, modulating and changing it as the gradient, or just rotating the sample, or that we have some distribution of pore in different direction. You can get information because along this axis of the capillary, you have the bright region. Here you have dark region, and from here, for example, you can get simple formation of the Bolat vessels or nerve system. We have applied also these techniques to test it for the polymers. Theory said its spectrum here is dependence on the molecular weight and the frequency. According to theory, it should be flat. But we see that it's not flat. We get something else. We've been able to explain it. But it's more surprising. We apply the techniques for normal liquids, water. In water, we get quite strange result. Instead of completely flat, we get dependence, but it depends on frequency as well as echo time. A shorter echo, a short time, you have different. We don't know how to explain it, and theory is not behind. There's some explanation. This has been done on a mixture of glycerol and water mixture. We can go also something else. It is quite unexplainable. We don't understand it. And I came to the conclusion, since to me I don't want to repeat it, this is what I already said before, so thank you very much for your attention.
Thank you so much for this fascinating lecture. I think we have a minor technical issue, so don't worry about what is happening here. Let's focus on our speaker. So, are there any questions from the audience? Greg.
That's me. Thank you very much. I have a very specific technical question. And this is, you are using CPMG sequence, but if you turn on the gradient after the 90-degree pulse, it's not longer the real CPMG sequence, because it's Y for a couple of those spins, but it's still X for the others. Do you really care or not?
No, actually, no, we didn't care. We simply CPMG sequence, simply properly, just exactly CPMG sequence. And the gradient, there could be problem at the very beginning, because with the first pulse, with 90-degree pulse, in such a system with strong gradient, you also excite the region. Yeah. And also the measurements depends, you measure just measure the diffusion in this small region, narrow region. We have done this in the maximum was 20 Tesla per meter, so the slice we measure was just a few microns, something like that. But you can also measure the wider region, but should apply, you can simply switch the gradient at the very beginning, before this p-pulses appears.
Okay.
Some people said that maybe p-pulses can make some slice selection. It is not correct. Samo Lasic, he's here, he has shown that this p-pulses doesn't affect at all, because spins are moving around. Only what happens, this I shown you, this resonance offset effect might appear. So that p-pulses does not affect slice selection. Oh, yeah.
Thank you.
Hi, beautiful talk. I wonder, have you ever tried to measure next order terms in this cumulant expansion of Kubo at the function of frequency, like kurtosis that frequency dependent and so on?
Not, I said at the very beginning, just calculations show you that problems appears when displacement of particle is too large. A gradient produce phase grating. It means that after each turn around, this is called the phase grating. And if the displacement is smaller than this phase grating, you don't care of whether it can be calculated such a way. This turbulent expansion is perfect. Gaussian approximation is perfect, especially in our case, even that we are applying the very strong gradient pulses, but because we are switching very quickly. And the time of switching, displacement is always smaller than the phase grating.
Well, but the higher order terms obviously exist, so they can be probed. The question is, have you tried to look at them?
For example, comparing the propagator method and that one, you can find in the calculation that there appears just a small difference. Just a small difference, yeah.
Yeah, it is small, but it's interesting.
It is shown by Ole Soderman. They measure this diffuse propagator method. Actually, seems to me, they found that it has a form of pyramid. But you can do, but also seems to me that approach through the simply. Maybe we can discuss it later. Okay?
Sure.
Okay.
Are there any more questions from the floor? Come on. Yeah.
Janez, thank you so much for that wonderful talk. Just a question about what do you prefer in principle, frequency measurements or time-dependent measurements, because they would probe different things, and do you combine them, or do you consider the frequency to be sufficient?
You actually also use this formula for pulse gradient techniques, yeah. But you can see that expression is very complicated. It doesn't give you simply, but it is some, if you look to the papers, it is difficult to extract for pulse techniques information directly of the motion. It's a mixture because in this dependence spectrum, actually the pulse gradient covers the low frequency range. And you get integral of this low frequency range. So you do not measure exactly the value of the spectrum, but measure just integral of the spectrum according to a certain range, something like that.